Welcome to Science Manthan. Let's talk about one of the most familiar yet completely fascinating substances around us, water. We drink it, we cook with it, we wash with it, and, well, we watch it fall from the sky. But water has this truly magical, shape-shifting nature that we interact with every single day, often without even realizing it. I mean, really think about this for a second. How can one substance exist in three completely different forms? The solid ice keeping your drink cold, the liquid water you're actually drinking, and the steam rising from a hot cup of tea. They are all the exact same substance. It's kind of mind-bending when you stop to really think about it. Okay, let's dive into this. Today we're looking at the three states of water, how melting and freezing actually work, the magic of evaporation, what speeds that process up, and finally, why evaporation causes things to cool down.
Section 1. The three states of water.
So we need to lay down our foundational states of matter as they apply to our shape-shifting friend here. We essentially have three physical states. First up, the solid state, which we all know as ice. It has a definite shape. You can pick an ice cube up with your fingers, and it absolutely does not flow. Then we have the liquid state, just regular water. It has no fixed shape, right? It effortlessly flows to occupy and fill whatever container you pour it into. And finally, the gas state, known as water vapor. Now, the absolutely crucial point here is that water vapor itself is entirely invisible. It just spreads through the surrounding space unseen. Sometimes you see a mist above boiling water, but those are actually tiny liquid droplets that have cooled down, not the invisible vapor itself. So those are our three foundational forms. But of course, water doesn't just sit still. Section 2. Melting and freezing explained. This is where we get into the verbs of our explainer, how water actively moves between these different physical states. Imagine melting and freezing as a giant energetic tug of war. On one hand, we have melting. This is where you take solid ice, you add heat, and it gradually becomes liquid water. On the flip side, we have freezing, which is the exact inverse process. You take liquid water, apply cooling by removing that heat, and it locks right back into solid ice. It brilliantly illustrates this perfect push and pull relationship. You apply heat to melt, and you apply cooling to freeze. Section 3. The magic of evaporation. Now, this is perhaps the most complex and interesting transition. To really get it, I want you to solve a little mystery with me. When it rains and leaves a big puddle on your street, where exactly does that water go when the sun comes out? Well, evaporation. It's the process where liquid water changes directly into water vapor and enters the surrounding air, even without boiling. I really want to highlight that last part for a second. You don't need a rolling boil on a stove for this to happen. It happens gently, right from the surface of exposed liquid water, just by absorbing ambient heat from the environment. To help you visualize the science happening all around you constantly, just think of these everyday examples. Wet clothes drying on a clothesline out in the yard. A freshly mopped floor that slowly becomes dry as you walk away. Those rain puddles we just talked about gradually disappearing from the pavement. Or even sweat vanishing from our own skin after a heady workout. In every single one of these sensory experiences, liquid water is quietly transforming into invisible water vapor. Section 4. What speeds up evaporation? You might have noticed that this process isn't always consistent. Ask yourself, why do your wet clothes dry way faster on some days compared to others? There are a few controlling factors at play here. The first factor is surface area. Spreading water out just gives it more room to escape into the air. If you have equal amounts of water, but one is spread across a wide plate, you have a larger surface area, which means faster evaporation. But if you have that exact same amount of water crammed into a narrow container, it has a smaller surface area, so the evaporation struggles and is much, much slower. The water molecules literally just need a clear exit path. Now, what's really interesting about this is how temperature acts as a massive accelerator here. A high temperature, like on a blazing hot summer day, pumps energy into the water, resulting in much faster evaporation. Conversely, a low temperature on a cold day means less energy and therefore slower evaporation. Heat is the essential fuel that drives this change of state. Next up is moving air. I want you to picture a really windy day, drying your wet clothes on a clothesline in record time. Why does that actually happen? Because a breeze or a fan literally sweeps the newly formed water vapor away from the surface of the wet object. By clearing away that humid layer of vapor, the moving air makes room for more liquid water to evaporate, helping surfaces dry much, much more quickly. The final factor is humidity, and that's just how much water vapor is already present in the air. This has a strict inverse effect. If there's high humidity, meaning the air is already totally full and crowded with water vapor, evaporation slows down significantly because the air just can't accept much more.
But if there's low humidity and the air is nice and dry, evaporation can happen much faster.
Section 5. Why evaporation causes cooling.
Okay, we've reached the absolute coolest part of this process, literally, revealing a truly fascinating physical side effect. Think about this. When sweat evaporates from your skin, it takes heat away from your body, producing a cooling sensation. Isn't that brilliant? Our own bodies use the laws of physics as a built-in air conditioner. The sweat itself isn't what cools you. It's the physical evaporation of that sweat drawing heat away from your skin that actually gives you that relief. And humans have harnessed this natural cooling effect for centuries. Think about traditional earthen pots. They use this exact same science. Water evaporates through the tiny, microscopic pores on the outer surface of the clay pot. As it turns into vapor, it takes heat with it, effectively cooling the remaining water trapped inside. You can also see this principle at work when water is sprinkled on a hot surface to make it feel cooler. It's incredibly smart, low-tech engineering based purely on the principles of evaporation. Let's move to and see how this builds our final understanding. Just a really quick recap of the 3 critical transitions we explore today. Step 1, melting, taking us from a solid to a liquid. Step 2, freezing, bringing us back from a liquid to a solid. And step 3, evaporation, lifting us from a liquid into a gas.
So now that we know how water changes state right here on the ground, how exactly does evaporation help create the clouds in our sky and the rain that falls back down to Earth? That is a pretty provocative thought to leave you with, and we'll explore exactly how water moves beyond our surroundings next time. Like, subscribe, and share for such more science-related videos. Also, drop your comments and queries in the comment section. We will catch you in next one.